Welcome back to part 2 of the lecture about fundamental counting principles. So in the first part, we talked about when you're allowed to use the fundamental counting principle versus when you're not allowed. And you have to have the uniformity idea. In other words, your second or third or fourth choice, how many options you have for that cannot be affected by what particular option you selected for the previous choice. So we're going to have to keep that in mind. But as long as you have the uniformity principle, you're allowed to multiply how many ways you can do each task. And so in example F here, in some states, auto license plates have contained 3 letters of the English alphabet followed by 3 digits. They want to know how many license plates are possible. So let's think about how do you build a license plate. Well, for this state, it's 3 letters. So I have a letter, a letter, a letter. Okay, so letter. I think it always helps to label what your task is. Letter, letter, letter. And then it said followed by 3 digits. So I have a digit, a digit, a digit. So remind myself, digit, here's a digit, and here's a digit. Now, things we need to think about. Does it matter if I select a letter here, does it matter how many options I have here? Well, yes and no. It depends on if you reuse or not. That's one thing we've got to think about. But does what letter I pick here affect the number of options here? And the case is no, actually on both of those. This doesn't say anything about you can't reuse. So if we wanted this to be, BBB 333, we could certainly do that. Okay, it doesn't say you can't reuse. And it doesn't say anything about this is not uniform, because if you pick a B, then you can only pick something here. But if you pick a K, you can have a different amount here. No, that's not the case. So this is about as basic as it gets. How many letters are there in the alphabet? Well, we know there's 26, right? So to pick the first letter, I have 26 options. You know what? To pick the second letter, I also have 26 options. Why? Because it's still the same alphabet. And again, we're allowed to reuse the letters and the numbers for our tag. So we have 26 options for the third letter as well. Now, digits, how many options do you have? Remember, you're talking 0 through 9, which is actually 10 numbers. Count them. So you realize 0 through 9 is 10 numbers. And since, again, we can reuse the numbers, then there you go. 26 times 26 times 26 times 10 times 10 times 10, which gives you a whole lot of license plates. I'm typing it in now. And that's large. Let me write the number down first, and we'll talk about it. 17576 and 3 zeros. So when you put your commas in there, notice that's 17,576,000 possible license plates. And that would include something like BBB 333. Now, if it said we couldn't reuse letters or we couldn't reuse numbers, it would be a different calculation. But if you can reuse everybody, then there you go. Here's another problem that it's really worth it to pause this one. So, Butler County license plates. And by the way, this is not the only license plate you can buy in Butler County, but this is an option. They have 7 characters. Okay, so we already know we've got 1, 2, 3, 4, 5, 6, 7 characters. That builds a license plate. Now, it says the first 2 characters are a 0 and a 1. I read that backwards, a 1 and a 0, and that represents Butler County. So we know we're going to have a 1 right here and a 0 right here. We know that for fact. Now, again, just so you know, all Butler County license plates aren't done this way, but this is an option. And then it says that's followed by 2 letters. Okay, 2 letters. So you're going to have a letter and a letter, then 3 numbers. So you have a number, a number, a number, right? It doesn't say anything about you can't reuse the numbers or the letters. So here we go. How many letters are an option? 26. How many letters are an option? 26. How many numbers? There's 9, 9, 9. Because if you're talking 0, not 999, my bad. 0 could be included, right? So 10, 10, 10. Anytime you can include 0, that's 10 digits. Now we multiply all this together. Now be careful, y'all. Real quick right here. That's not how many ways you can do it. That's just fixed, a 1 and a 0. I really should have put it underneath. That's a 1 and that's a 0. There's only one way you can pick a 1 and only one way you can pick a 0. Now you can multiply all those together. Okay, so 26 times 26 times 10 times 10 times 10. And that's going to be big. Not as big as the problem we just did. So that's 676,000 options. Now, there are not that many people in Butler County, so we're not going to run out of possible license plates with the 1 and the 0 using these rules. Okay, so we have a story about Vern. He has 4 antique golf clubs that he wants to give to his 3 sons, Mark, Chris, and Scott. How many ways can the clubs be distributed? So I had to read this problem a couple of times to think about what in the world are they asking. So, again, Vern, he wants to give his 4 golf clubs away, right? And he wants to give them to Mark, Chris, and Scott. Now, notice there aren't any restrictions on this question number 1 for H. So, if he wanted to give them all 4 to Mark, he could. Or give 3 of them to Mark and 1 of them to Scott, and Chris gets nothing. He could. It doesn't say that that's not an option. So, when you think about doing this, here's what I want you to think about. The tasks are giving away the 4 golf clubs, not the 3 sons. It's the 4 golf clubs. So task number 1 is giving away golf club number 1. Task number 2 is golf club number 2. Task number 3 is golf club 3 and golf club 4. Are you with me? So again, this is golf clubs. Now, each one, separate golf club. So for the first golf club that you pull out of the bag, okay, how many options for giving it away do we have? Well, it could go to Mark or Chris or Scott. Right? So that's 3 different options for the first golf club. Now for the second golf club, he could also give that to Mark, Chris, or Scott. Because it doesn't say anything about how they're distributed. Again, it could go to Mark twice, so repeats are fine. The third golf club, how many ways? Well, 3, right? Because it could go to Mark, Chris, or Scott, and Mark, again, could end up lucky with the first golf club, the second golf club, the third golf club. And you know what? He could even end up with the 4th golf clubs too, because it doesn't say anything about a restrictions. So if you multiply 3 times 3 times 3 times 3, which by the way, you know that's 3 to the 4th, right? It's going to give you 81 possibilities. If you organized it every way you possibly could to distribute these 3 golf clubs, then that would be the way to go. Now, what Vern should do probably is give 1 to each of them, and then the 4th golf club maybe go to the one that got the worst of the 3, or the one that plays golf the most, or, you know, something strategic. But if you don't have any restrictions, then, yep, Mark could end up with all 4 golf clubs. But now look at the next question. There's some restrictions going on here. How many choices are there if the power driver must go to Mark, and the number 3 wood must go to Chris or Scott? Okay, so we've got, again, the challenge of giving away 4 golf clubs. So these blanks are still the golf clubs. Okay, now, if you have a restriction, the smartest thing to do is to put the restriction first. We have probably already talked about this. But how many choices are there if the power driver must go to Mark and the number 3 wood must go to Chris or Scott? Let's put the number 3 wood first. Okay, and then next, let's put the power driver. So the driver is second. And then we can decide on the next one. So how many ways can we give out that number 3? It says the number 3 wood must go to Chris or Scott. How many options is that? That's 2, right? We only have 2 places the number 3 wood could go. It could either go to Chris or it could go to Scott. Now the driver, it says, must go to Mark. No other options. It must go to Mark. How many options is that? 1. 1 option for the driver. But now the other golf clubs, and by the way, it doesn't say what kind of golf clubs they are, but there are 3 sons we could give the 3rd golf club to, and 3 sons we could give the 4th golf club to. Okay? So when you multiply all that out, 2 times 1 times 3 times 3, well, we know 2 times 1 is 2, 2 times 3 is 6, 6 times 3 is 18 possibilities. Now, again, my advice is to put the biggest restrictions first. We could have even put mark first. That seems the biggest restriction in front of the options. That really makes a big difference if you can't reuse. But now we were able to reuse people for these two options. So the order we did this in doesn't matter as much as it does on some problems where you can't reuse possibilities. Okay? All right, example I. In how many ways can we arrange 6 pairs of shoes lined up in the closet floor? So basically, you have your closet wall right here, and we're doing 6 pairs of shoes. Now, we're keeping the pairs together. That only makes good sense, right? So you got pair number 1, pair number 2, pair number 3, pair number 4, pair number 5, and pair number 6. Okay, we're going to line them up against the wall, so we can just go in there and grab a pair when we need it. Now, the question is, how many ways can we do this? Well, let's think about it. To put it on the first spot along the wall floor, you got 6 pairs thrown in your floor. How many ways can you pick a pair to go in the first spot? How about 6 ways? You got 6 different pairs of shoes to choose from to go in that first position. Then you're going to sit another pair next to it. Do you have 6 different ways to pick shoes for the second one? Well, no, because you've already put a pair right here, right? That pile behind you is now 10 shoes or 5 pairs. So you have 5 choices for the next position. And then sitting next to those first 2 pairs, you have 4 choices out of that big pile of shoes you have back behind you. There's only 8 shoes left, which is 4 pairs. Now that you've already got 3 pairs lined up, you got 3 pairs back behind you to choose from for the 4th spot, and then 2 pairs behind you for the 5th spot. And then right by the time you get here, you better only have 1 pair of shoes left, and so there's only 1 way to pick that last pair. So that's how many ways. Now, remember, this is a multiplication step. You multiply all these values together. 6 times 5 times 4 times 3 times 2 times 1. And that gives me 720 ways. 720 ways to organize 6 pairs of shoes. That's fun, isn't it? Now, what you're doing here is arranging. Key word here is arrange. Anytime you want to arrange something, we have a formula for that, okay? And it's called something special, but just give me a minute because I want to show you a brand new mathematical term that maybe you've seen before, maybe you haven't, but check this out. It's called a factorial formula. So it says for any counting number n, the quantity n factorial, that's the way it's read, n factorial is defined as, and again, this notation right here is read, it looks like an exclamation mark, I know, but it's read n factorial. And what it means to do is multiply a number times the number less than that, times the number less than that, times the number less than that. So, for example, 8 factorial is 8, let's start with 8, times 7, times 6, times 5, times 4, times 3, times 2, times 1. That is what 8 factorial is. Now, why did that come up just now? Look what we just did. 6 times 5 times 4 times 3 times 2 times 1. I could have wrote that as 6 factorial. And that would be easier. And, of course, you can find that in your calculator where you wouldn't have to type in 6 times 4 times 3 times 2 times 1. You could just type in 6 factorial, and it's going to tell you 720. Okay? Now, I have to give you a definition of 0 factorial because, you know, factorial is all about counting. So 0 factorial is just weird. So, by definition, we need 0 factorial to be 1. So, anytime you have done some calculations and you get 0 factorial, again, that is equal to 1. Now, let's do some calculations with factorial. You want to? So, you'll see at the bottom here, I want you to evaluate 3 factorial. That's 3 times 2 times 1. Of course, we know 3 times 2 is 6 times 1 is 6. 15 factorial, on the other hand, is large. 15 times 14 times 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, this is when you probably ought to find that button on your calculator, okay? Because 15 factorial is big, and if you'll notice below that is 25 factorial, which is even bigger. Now, I'm going to type that in my calculator and show you what I get. And look at this. So it gives me 1.307. I'm going to write down everything that showed up in my calculator. 674,368. And then it has a little bitty 10 to the 12th. Y'all know what that means? That's scientific notation. And it means to move this decimal place 12 places to the right. Can we do that? Sure we can. So first of all, how many places is it if I move it out just to the end? So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Now to get 12 to 12, I got to add 3 more zeros. So the answer to this question is 1307674368000. And I put my commas. And this is an enormous number, So, of course, these are the hundreds. These are thousands. That's 368,000. These are the millions, right? What comes after millions? Billions, right? And then trillions. So this is 1,307,674,368,000. That is an enormous number, and that's just 15 times 14 times 13 times 12 times 11 times 10. You get the point, right? That's 15 factorial. Now, why do you think my calculator did something crazy like what it did? Why do you think it did this? That times 10 to the 12th business. Well, calculator, the screen is only so big, and it'll only hold so many numbers, and so that's the way they handle it. So if you've got a really big number like that, it does times 10 to some power, and then there you go. Okay? Now look at this next one. To the point after the one we just did, you might not even want to do it. And I might not have space to do it, but I'm going to show you a trick and we'll get to try it again. So 25 factorial, okay, over 3 factorial times 20 factorial. Now let me tell you something. 3 factorial times 20 factorial is not 60 factorial. You can't do that. But let me show you something you can do, which is pretty awesome. Remember what factorials are. 25 factorial is 25 times 24 times 23 times 22 times 21 times 20. But look, I'm going to write factorial, because 20 factorial just means you keep going down. Now, I stopped at 20 because I noticed there's a 20 in the denominator. And 3 factorial, I'm going to write as 3 times 2 times 1, and then times 20 factorial. Now, again, you may see exactly what's going to happen. I'm canceling that 20 factorial with that 20 factorial. And then I'm going to type this in my calculator. 25 times 24 times 23 times 22 times 21 divided by 6, because 3 times 2 times 1 is 6. And when I do that, the answer I get right here at the bottom is 1062600. Go put the commas in. That's 1,062,600 for L. So we have a neat trick that's going to come up a lot. If you have big factorials, especially if you're dividing, you write your top one down till it matches the biggest one in the bottom, and then you can cancel those, and you don't have to worry about so much multiplying. And my suggestion is you pause it, work these out, and see how it goes. These are common problems that students make mistakes on, so I just want to make sure you're comfortable with it. But pause it. See if you get the same answers I get. When you come back, you can watch me do this. So 4 factorial is 4 times 3 times 2 times 1. We could even do that in our head. 4 times 3 is 12. 12 times 2 is 24. 24 times 1 is 24. So 4 factorial is 24. But 8 factorial is a lot bigger. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And that's just going to be a calculator situation. And I got 40,320 for 8 factorial. Now here, notice the parentheses. You don't go 8 factorial minus 4 factorial. That's what this last problem on the top row is. 8 minus 4 factorial is the same as 4 factorial. Just do in the parentheses first. The factorial is on the outside, and we already know 4 factorial is 4 times 3 times 2 times 1, which is 24. Now, 8 factorial minus 4 factorial, well, we've already calculated 8 factorial, that's 40,320. And we've already calculated 4 factorial too, that's 24. So I take that 40,320, subtract 24, and get 40,296. Now, when you look at the bottom row, you've got 8 factorial over 4 factorial. We know a trick, don't we? Anytime you have factorials in the numerator and in the denominator, and there's no addition or subtraction going on, it's just multiplication, you write the top factorial all the way down to the biggest factorial in the denominator. So notice I wrote 8 times 7 times 6 times 5 times 4 factorial. And in the denominator, I have 4 factorial. Now what happens is that 4 factorial cancels with that one, and my answer is just 8 times 7 times 6 times 5. And that's 1,680. Now, this is different. This is the fraction 8 fourths factorial. Y'all, that 8 divided by 4 is 2 factorial, and 2 factorial is 2 times 1, which is 2. And then the fun one, 5 minus 5 factorial, that's going to be, 5 minus 5 is 0 factorial, and 0 factorial, remember, it's not 0, it is 1. So let's get back to why you might need this factorial business. Remember arranging shoes in the closet? And if you have 6 different pairs of shoes, there's a gazillion ways you can arrange them by doing 6 times 5 times 4 times 3 times 2 times 1. Well, that's exactly what we have going on here. So arrangements, if you're ever trying to arrange something, you know, a lineup for class pictures or something like that, then there's going to be n factorial ways to do that. And it really just comes from the tasks and using up one, and that's why the numbers go down each time. Now, what if you have repeats? Okay, and this is when it gets a little bit interesting. What if you have repeats? So the number of distinguishable arrangements of n objects where one or more subsets consist of lookalikes, say n1, or one of a kind, or n2, or of another kind, you end up dividing by the factorial. Now, it's going to help you to see a problem that uses this, so you know what I'm talking about. So, we already know about the arrangement situation. So again, what if you wanted to, let's go to the orange, what if you wanted to arrange, you know, 10 classmates in a picture? Well, the answer to that is just going to be 10 factorial. If you're going to line them up straight, there are 10 different ways you can pick the first person, and that first person stays in line, and then 9 different ways to pick the next person, and then 8, and then 7, and all the way down. So 10 factorial is big. I'm not going to even calculate it. But what if there are repeats in there? And if you're doing class pictures, there are no repeats in that situation. So that's what the yellow is talking about. So I want to pull up an example to show you what I'm talking about, and then we'll see if we can't use this idea. Okay, so it says think about the arrangements of the word mom. Just the word mom, M-O-M. How many ways can we rearrange those letters? Okay, now let's think about it. You could start just every possibility. You could try to list them, right? I'm going to call this M1. Uh-oh. Not unless I get my pen working. I'm going to call this M1 and this M2. Okay. So, one of the options is just as it is. So, M1, 0, M2. Or, you could stick the M1 there, and you could rearrange the M2 and the 0. Okay. Is there any other way the M1 could be first? I don't think so. Alright, so now, let's let the O be first. So then I would have O, M1, M2, or I could have O, M2, M1. Now let's let the M2 be first. So I could have M2 and then O and then M1, or I could have M2 and then O and then, M2, M1, and then O. Again, I'm just trying to rearrange all of these letters every way possible. Now, let's think about it in terms of a task. Okay, so remember arrange. If I use this first rule right here, the arrange is just n factorial. N is how many letters you have. It's 3 factorial. So 3 factorial equals 3 times 2 times 1, which is 6. Or if you think about it, the way we've been doing it this whole lecture is in terms of task. So task 1 is to pick the first letter. How many options do we have? An M, a 0, or an M. So 3 options. How about picking the second letter? Well, we've already picked the first letter, so when you pick the second letter, you have 2 options. And picking the third letter, you have 1 option. So that's going to be, again, 6. We've got all the possibility listed, okay? But here's the deal. Some of these are not different. If you were playing Scrabble, y'all, this mom and this mom would not be any different at all. If I've got an M and I've got another M, it doesn't matter which one M I did. Mom is mom. That's what they mean by repeats, okay? So if we use this formula, we would have the 3 factorial on top to represent the mom arrangement, but then you would divide by your repeats. Well, M repeats. So we divide by 2 factorial, and 3 factorial divided by 2 factorial is going to be 3 times 2 factorial over 2 factorial. The 2's cancel and I just get 3. So let's get rid of the matches, like mom and mom, that's the same, so I'm going to get rid of that one. Okay, and look, ohm and ohm, one of those is the same, so I'm going to get rid of that one. And then M1, M2O is the same as M2, M1O, so MMO and MMO are the same. What does that leave me with? If I circle what I have left, maybe I didn't get rid of, that is 3 options. I was nervous there for a minute. That's 3 options. So anytime you can't distinguish between some of your outcomes, you have to divide those out. So let's do a problem real quick that expresses that and then call this video done, okay? All right, so determine the number of distinguishable arrangements of the letters in each word. So this is really like 3 different problems, okay? And again, it wants distinguishable arrangements. So what I'm really trying to do is rearrange the letters of Florida in every possible way that I can, okay? Now, we could do our task, right? The first position, second position, third position, fourth position. The real question is how many positions do we have? Well, there's 1, 2, 3, 4, 5, 6, 7 letters. I swear I picked the pen already. Okay, right here, 7 letters. Do any of those letters repeat? They don't. I don't see. The F is not there again, the L is not there again, the O is not there again. You get the point. So to arrange all of these, just like shoes in the closet, I'm just going to do 7 factorial. And 7 factorial is 5,040. Okay, 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, let's try the next problem. So do me a favor, while I pick my pen, you count how many letters are in Alabama. Okay, so A, L, A, B, A, M, A. That's 1, 2, 3, 4, 5, 6, 7. Turns out there's 7 letters again. Now you might be going, wait. Stuff repeats. That's what you divide by, right? So there's 7 letters, so that's 7 factorial. But since what repeats? The A. The A shows up 4 times. So if I rearrange those A's, I'm not going to be able to tell which one's the first A, the second A, or the fourth A. Those are not distinguishable. So what I'm going to do is I'm going to take that Alabama and 7 factorial and divide it by the number of repeats of the A, which is 4 factorial. Because it's going to knock it down a lot smaller, right? So it's going to be 7, hey, I got to simplify this. So 7 times 6 times 5 times 4 factorial. Remember, always go down to the biggest one in the bottom. You keep the 4 factorial in the bottom and cancel that 4 factorial and that 4 factorial. And then you multiply 7 times 6 times 5. And there's only 210 different ways you can arrange those letters. It's really 5,040 ways to arrange the letters, but a lot of them you're not going to be able to tell the difference. Because if I say A, and then LBM, there's so many different ways I can get that because it depends on what A is in front. We don't want to count those multiple times, so that's why it's just 210. And then, just to make sure you know what you're doing, I gave you Mississippi. Okay? So pause it. You work on Mississippi, and come back and let me know what you figured out. Alright, so first of all, we've got to figure out how many letters are in Mississippi, right? So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Do you see that? I don't have my glasses on because they keep breaking and falling off my head, so it's all blurry to me, but I think there's 11 letters. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yes, 11 letters. So that means if we want to arrange all those letters, we've got to calculate 11 factorial. Again, 11 times 10 times 9 times 8 times 7 times 6. Hey, but there's some repeats, right? Now, M is not a repeater, so I don't have to worry about M. But look, I shows up 1, 2, 3, 4 times. So we need to divide by 4 factorial for the I value. Hey, but that's not the only repeater in the bunch, right? What else repeats? Oh, I see some S's. So there's 1, 2, 3, 4 S's that repeat. So I have to times that by 4 factorial. So that represent the S's. Is that the only thing that repeats? Nope. Got a couple of P's, right? So PP, there's 2 of them, so I divide by 2 factorial, and that represents the P. You okay with this? So again, 11 letters, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 factorial is the way to arrange all of those. But so when S and S are together, you can't tell which S is which S. Therefore, we want the distinguishable arrangements. We need to divide by those repeats. So there are 4 I's. That's why I put this 4 factorial. There are 4 S's. That's why I put that 4 factorial. And then there are 2 P's, and that's why I put the 2 factorial. Now I need to calculate this. Now, how do you do it? You take the top one and write it down to the bottom one. So I have 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 factorial, almost didn't fit on the page, divided by 4 factorial times 4 factorial times 2 factorial. One of these 4s, not both of them, y'all. One of the 4 factorials will cancel. Now, just for the sake of space, I'm going to get rid of Florida over here, okay? 5,040 is going to go. We're going to continue on with Mississippi calculations. So in the numerator, I've got 11 times 10 times 9 times 8 times 7 times 6 times 5. In the denominator, right here, I still have 4 times 3 times 2 times 1. That's the 4 factorial. And then times 2 times 1, that's the 2 factorial. Now, if you wanted to, you could cancel more stuff. Like I see this 3 and this 2, that's going to cancel with 6. And I see this 4 and this 2, and that's going to cancel with 8. It makes my numbers a little bit smaller. Or if you've got a calculator in front of you, why bother doing all that? Just type it in. Okay, so I'm going to type in 11 times 10 times 9, but I canceled the 8, so times 7, I cancel the 6, times 5. And when I do all that, I get 34,650 distinguishable arrangements of Mississippi. Fun, huh? So I hope you have a good day. Please let me know if you have any questions. I can always do an extra video to fill in any gaps or any homework problems that just don't make a bit of sense. So y'all have a good day.